I'm postdoc at data science team at ALCF, and today I'll be speaking about profile and deep learning. We have 1 hour for this section, and it is split between different subsections. We will speak about. I will speak about profile and deep learning in general at the beginning, and after that we will have two subsections. One is the example of profiling PyTorch scripts, and another one for profiling TensorFlow. So in the presentation, we'll be speaking about profile in general, and most importantly, motivation for profile. I will try to convince you that sometimes fine tuning is not necessary and even can be not a good choice. We will speak about some frequent problems in profiling and common profiler APIs, and I mentioned just some important things for output of profilers. So basically, profiling, it is a process when you just run special utility with your script and you measure execution time, memory allocation, and everything inside the script. And you can make any marks, so you can even measure the piece of code which you want. And for instance, there are different views of profiling. Here you can see a view for profiling in just terminal, which is quite common and often used. And another view is TensorBoard. It is nice dashboard. TensorFlow had it for a long time, but PyTorch only recently introduced it. So since PyTorch 1.8, we have this nice dashboard. So it summarized everything. Um, Now let's speak about motivation to profile. So the main question is, what is the purpose of profiling and what you want to get from the profiling? So there are different answers for that. The first one is finding performance issues, and I think this is the most important point. So sometimes your program is not linked correctly, and your script does not call some optimized backend, or it's possible that you have some intuition that, for instance, how much time should spend in multiplication of matrices, but in practice, in reality, you did something I would say not good, and actually this results in some performance issues, severe performance issues. And with just profiling, you can understand that everything is going okay, or you have some problems. And usually, when you have some problems, you can solve it, and this will speed up your program maybe 100 times or tens of times. So I think that this is a more helpful thing. Another point is optimizations and tuning. And so if you want to deploy your model, or for some scientific task, you just created a model, train it, and now you want to just to deploy it in your code, and this executed a lot of times. So if you really optimize it, you will have really huge speed up. But in this case, you have already trained model. And the final question is fine tuning. And I personally think that it's usually not necessary and even bad thing, since you spend a lot of time on just getting just few percent of optimizations. And in this case, I want to mention the Donald Knuth, who says that premature optimization is the root of all evil. And with profiling, you can really understand that something is going wrong with your program, and you can easily solve it. Or you need really some optimizations and more deeply understand your code, more deeply do it. Um, do you need to deeply profile and optimize your script? So it depends on the task what you are doing. So if you, as I said already, if you have trained model and you want to just deploy it, of course you can profile and optimize it in a good way. But if you do it in training, it's another question. So for training, for some problem, you do not know architecture, you're trying different things, different ideas. And if you really fine tune one architecture, it will not be so great for another architecture. But there is a list of some things which I would say some good practice. And if you, with the profile, you can understand that this is going good. And if it works okay, it will work for any architecture. So now I'm speaking about, for instance, IO operations or some copy operations. So if you profiled your code with just one architecture, understand that you have fast IO operation, you have correct memory copies. After that, you can just change architecture and you will know that your program will be working more or less good. Um, Another point that with optimization, sometimes people just trying to optimize more and more. And there is one example with batch size, for instance. So not all models have increasing accuracy, and sometimes it's even suffering in accuracy. So accuracy decreasing if you increase batch size, but you will have better performance. But basically, your problem will not be solved because you will have less accuracy. And finally, I would like to mention that you always have to take into account your efforts for optimizations. And the first thing which you have to do just to check utilization of GPU, you can easily do it with NVIDIA SMI. And nowadays, GPU is a really big one. And to load it correctly, you need just increase batch size. Sometimes the batch size should be really a huge one. After that, if you want to optimize more deeply, you need to estimate somehow that if you are going to get some huge improvements and you're going to spend a lot of time and get just few percent of performance. And always you need to understand that optimization, really fine tuning takes a lot of time, and you can gain just few percent. And opposite, if you have some bottlenecks, you can easily solve them, and it will speed up your code just hundreds of times. Um, there is a list of some common problems for scripts. The first one is I/O operations, and so for instance, when people just try different problems, they can load data, and they can create their own functions alone with NumPy operation and so on. So this is actually bad practice. There are good data loaders in TensorFlow and PyTorch, and they're really optimized. And if you use it, you can uh, you can tune them a lot. So for instance, there is a possibility to use multi-threading, so you can just increase number of working, and you will have much better IO operation like for free. You do not need to write your code for that. Um, Another possibility is that you need to think about IO operation that maybe you can just load everything at the initialization stage, and you do not need load at every iteration. The second problem is copy operation. So you probably know that the copying is much slower than computation, and quite often it could be happen that when you create some model, you know this you have the set some mathematical operations, and NumPy has a really great library for that. But unfortunately, deep learning library doesn't have it sometimes. And the easy thing just to move tethers to CPU to NumPy, do some linear algebra you want, or some other things like decompositions, solving determinants, everything that you want. And after that, move it to GPU onto PyTorch. This is fast solution and will allow you to create a model. But in practice, usually people underestimate how much time it takes, and usually it causes some severe performance problems. Often it's possible to rewrite this code in such a way that you will do everything on GPU. So either you modify algorithm a little bit, or you can use libraries like Numba or CuPy, which can do everything on GPU directly. There is also a possibility between overlapping copy and communication. So, for instance, you run the copy for first iteration, and you can run computation for previous iteration in this case. And when you go to another iteration, you will have data because you ran copy before that. And you can use a synchronous copy and so on. There is also problems with batch size, and sometimes it can be too small for GPU, and just increasing the batch size will result in high performance because you will load GPU more efficiently. And finally, it's possible to optimize your script with decreasing precision. It's becoming more popular now, and it's common that for many models, you can just decrease the precision from double to float, from float to half, and you will have much better performance for that just because you have like less data, you need less copy and to do less operations. And in deep learning libraries, there is after tuning mechanism. For instance, in PyTorch, you can just run context manager, and it will do some uh, performance benchmark at the beginning, and it will figure out the best precision for your task and the best performance. So in this case, you almost getting like speed up for free. Um, Usually, profilers have some common APIs. And for instance, you can run Profiler as a context manager. And as you can see here on the left, so basically you just run Profiler, you can set additional flags which you want, like in this example, you set activities like CUDA and CPU. There is some additional things, and inside you just run some model and some operation which you want to profile, and the output you will see results of that. Another possibility is use decorators, and with decorator just decorate the function which you want to profile, and in the output you will see results for that. So it's quite convenient one. And finally, there is a possibility to run just submodules. So for instance, for PyTorch, there is a nice wrapper which called torch util bottlenecks, and you can just run it with your script without no modification of your script, and just to understand what is going on. So basically, it runs different profilers for you. Um, One thing I want to mention here is that there is some important difference between self CPU time and total CPU time. So basically, this is output of profiler from terminal. So there is different functions, and there is a metrics like self CPU time and total CPU time. And there is a main difference between that. If you measure the function, you can measure everything which is going on inside, and this will result in total CPU time. In opposite, you can measure only operations which you do with the data, and do not take into account calls of subroutines. And this will result in self CPU time. And from this, we can understand if what is going on in the function, if it does some work, or if it's just a wrapper. We can add any metrics here, so we can sort by any metrics and so on. So there are really flexible API for that. Finally, I want to mention new PyTorch profiler. So it was introduced just recently as a new tool, which will replace old profiler, and it has really nice dashboard. It's quite buggy now since it's new one, but it works more or less, and it's nice dashboard, so you can use it. So this is general view, and in execution summary, I want to stress that here we have some different sections for your code. So basically, it measures total time of your script, and under this total time, it measures different sections like kernel execution, CPI, and so on. And the point that these sections can overlap actually, and but they have to be summed to 100% totally. So in order to cope with this, it basically measured with the sum priority. So in priority is just same as it mentioned here. I just repeated here. So for example, if you run some your code and you have these operations like CPU execution, kernel execution, and copy memory, you start measuring, profiler start measuring with a measure kernel execution time, which in this example will be 5 seconds. After that, I have to measure mem copy operations, but actually it's overlapped with the kernel, and it's totally hidden on the kernel. So it will result in 0 seconds. Similar for CPU execution time, we have 2 seconds, but it's overlapped with the kernel, and that's why it will be only 1 second. So that's why when you see this execution summary, you can see like as a memory copy is like 0%, but in reality, it just overlapped with another operation. So we have like great overlapping of memory operation. So at this time, we switch to section on examples. And so I want to present some examples for PyTorch profiling. Just let me share. Yeah. So if you go to our GitHub, there is like profile and frameworks folder, and inside PyTorch folder, you will see this tutorial. And in this tutorial, I'll try to summarize all possible profilers. There is a whole list of possibilities how you can profiler your application. So it's Torch Autograd profiler, which is basic and old profiler. New Torch profiler, which will remove old one. There is a Torch util bottleneck, and sometimes it's also convenient to profile your code with Python profiler. There is also Tau, actually. Tau really nice and great thing, so you can profile everything with the Tau. But for Tau, we had another section, so I didn't mention it here. You can run all examples on Theta, and basically in my tutorial, I have some really small and like brief examples just to demonstrate possibility of profiling. So the first example, we would like to analyze execution time. So we use just a model from Torch Vision ResNet model. And to run profiler, we just use a context manager. Here we just import Torch autograph profiler as a profiler and use it as a context manager. So as an output, you will see this result. It's different functions and metrics. So the important thing which we discussed before, that the CPU total time and self-CPU time. So this is ResNet model. So it basically is built from convolutions and some residuals. And we would expect a priori that the majority time should be spent at convolution operations. And from profiler, we see that indeed it's 80% of total time is spent there. But we can also see the code stack for convolution. So for instance, at the beginning, A10 conv to decode, but we can see that total CPU time is huge and self CPU time is small. It means that basically it's just a wrapper for another function. And it seems that it's called A10 convolution. And this process repeats again and again until we see ch and then conf to d forward function. Oops, sorry. Um, until we have this th and then conf to d forward method. And basically it does sum of work 30% of the time. And it seems that another portion of work around 50% is called just add multiply function. It takes 50% of the time. So basically in this example for backend, PyTorch just called native implemented method ch and then conf to d. You can also see like total CPU time. There is a point that we have a model, and for models there is a set of layers. And if you would like to know which layers take time, which layers have which time. So basically at this profile, we have only one conf layer, only one conf method. But if you would like to know for different layers, there are two possibilities. The first one is just to use labels, so we can label parts of a code which you want to profiler. But in this case, we use the pre-trained models and which was already built. So we can use another possibility, which basically we can track input tensor shape for every method, and we can sort by this input tensor shape. So in order to do it, we just need to use special flag record shapes, and in this case, it's recorded the input tensor shapes. So for instance, we can see that the first convolution for tensor shape 128, 64, 56, 56. So basically it is our input tensor. So it seems that it is the first convolution. And after that, it's just some call stack. And we see another, and we can see another convolution here. So it seems it's another layer and it has another different shape. So if you know the shapes of every layer, we can understand which layers takes which time. And in this case, it seems that first layer takes around 30% of the time, and the second convolution takes around 15% of the time. Another possibility just to measure memory allocation. So in order to do it, we just easily need to add special flag. And as the output, we will see again different functions, CPU times, and also memory usage. And basically we have self CPU and total CPU again, as we had before for, so we have self memory allocation and total memory allocation as we have for CPU usage. For this case, resize operation takes like allocates around 17 gigabytes of memory. Yeah, but by the way, it's a good question. So where this resize comes from? And basically, maybe you can play with this tutorial just to use flags, which we discussed in this tutorial, and try to understand from which layer this resize is called. I mean, from which method. Now let's try to think more carefully about our profiler. So I return a little bit back. So this is just our initial profiler of the script. And as we see here, so PyTorch called native algorithm CHNN cost2D. But we know that PyTorch is optimized for CPU, and backend for that is MKLDNN library, which is Intel library for Intel CPUs. But we do not see any calls of MKLDNN here, and it means that it's not used. And this actually is some example of some performance issues which you can easily solve and increase the speed of the code. There are different possibilities why it's not using. The first one that PyTorch was not linked with this backend, which you can easily try. And another one that basically this backend cannot be used. So we need to check documentation for that. And I already did it. And basically at official pages, it is written that MKLDNN can be used only for float precision. So basically, if we change precision for this script, we will see the following profile. And in this profile, we see that in this case, MKLDNN is called. So basically, we just change precision, and it takes like it does like 64% of total execution time. And the point here is that we decreased precision, so we could expect like twice increase in twice speed up. But the real speed up is a little bit higher, so it's 1.8 second against versus 5.7 seconds, so it's around 3 times, and it's because of optimization. So KLDNL. So it's highly depends on CPU and size of your task, but usually when you use optimized backend, it's much better. And this is nice example how you can use profilers, so you can easily understand if it's your backend, like CUDA, NVIDIA, and KLDNN is called sometimes even for communications like NCCL or MPI, what is called. Now let's switch to another example. At this example, we create some simple model. So we have module, and in this module we have some linear transformations, but basically it is a set of linear layers with activations. And in forward pass, we just calculate linear transformation. And after that, we sum our features and we interpret it as a threshold. So we mean it over batch size. And we want to know where some mask is bigger than this threshold. In order to do it, we can just we need to use argware, which basically returns indexes or where it happens. Unfortunately, PyTorch doesn't have this method, so that's why we move it to CPU and to NumPy and just calculate on NumPy. So at least my intuition would say that we have some linear transformation, basically multiplication of dense matrices, and just some comparison with just one comparison and the calculation of indices of it. So I would, so it's reasonable to expect that linear transformation takes most of the time. And in this case, we just check it with the profiler. So we use one label just for linear transformation, another label for masking, and run profiler. It's so we do some initialization, warm up, and run a profiler. Important thing here is also is warming up. So basically, when we run on a CUDA on a GPUs, PyTorch uses this really optimized library from NVIDIA, and basically it has several algorithms for convolutions. And during first execution, it just runs some benchmarking and picks the best algorithm which used for your problem, for your tensor shapes, and so on. So that's why the results of profiling will be biased if you just take it into account. So we skip it in the profiling. This is output of profiler. We see that basically the most time as a program, like 99.94%, is taken in the masking, and the linear path is just 0.05%, which is really small one. So it seems that something is going on, going wrong here, and so it seems that copy operations together takes like 15%. So we can easily optimize our script by at least 15% if you just remove these operations. And we can really do it. So we need to more carefully think about copy operations. And basically, we can just compare. We can compare a threshold with a mask, which will return a tensor of booleans, and after that, calculate method non-zero. And with special argument, it will just return indices of where it happens. So basically, we moved everything on GPU. And in this case, profiler shows that there is no copy operation. Linear path is also not so small. Linear path is also small. and non-zero operation takes most of the time. But the total speed up is actually huge. So before it was like 2.1 second, and now it's 6 milliseconds. So the speed up is more than 100 times. And it can be really interesting because we just removed 15%. So from our previous profiler, we saw that we just removed copy operation, we took 15%, and we didn't see anything else. So here we didn't see anything else which takes much of the time, but speed up was more than 100 times. And this is basically a problem of deployment profilers. So sometimes it just, not sometimes, just PyTorch profiler just measures uh, methods and functions from PyTorch and just ignores other functions. So in this case, it ignores NumPy argware function. And this is a problem, so sometimes it can mislead you. In order to avoid this, you can just run a standard Python profiler. And it can be also run as a context manager, so it's just few modifications in the code which you have to do. And when we run it with our example, we see that, so that's module Py, so some calling function, some forward function, and after that we see argware, so exactly what our problem is. And it's 1.7 seconds approximately, so it's actually, it was our bottleneck. And we speed up our script just because we were lucky. So we just wanted to eliminate copy operation, but in reality, we optimize our real bottleneck. This is a problem and can mislead you. So it's a good way just to start your profiling with just Python profiler. And but sometimes it can be confusing. So there is a thing which you can do just to run PyTorch bottleneck. This is can be run as a Python module. And basically what it does is just run your code with a different profiler. So it runs your code with a Python profiler and PyTorch profilers with for CPU and for GPU. And from output, you can easily understand where is your bottleneck. If it's some non-PyTorch operations, or if it's a PyTorch operation, you can more deeply have a look on PyTorch profiler. Finally, let's want just to mention the new PyTorch profiler. It can be also run as we did before, so with the context manager, we set activities here, like what we want to profile of CPU and CUDA operations. The nice thing here is scheduler. So in this case, we just set how many iterations we want to skip. It can be helpful if you have some lazy initialization in your code, and how many operations you want to warm up. So as we discussed for operations on GPU, and after that, how many operations you want to profile. After that, you, as we did before, run this profiler, and the important difference here is that you have to call prof step, so that it would know that this epoch is finalized. When it's ready, it creates data for this TensorBot plugin. You can run it as it's written here. So basically, in order to run it, you need to run it on a CETA GPU login node, and you need port forwarding from your local machine to CETA GPU login node. So basically, it's written here how you can do it, and you will have this nice view. I already did it. So let me open it. So basically, it's result of profiler. So as we discussed, there is a runs, which basically in this case, the name of a folder, workers. It is written in official documentation that basically it can be stacked with MPI. So if you have DDP, so every process will profile its own work, and you can see here the number of these processes, and you can examine every profiler. But in this case, we didn't do this. So we just measured a profiler for 4 iterations, and in total have 8 iterations. So we have 2 outputs, and profiler thinks that it's 2 workers, which is really not the case. So it's one of bugs I mentioned here. It is profiling for different epochs, so we can see in the execution summary, there is different views like operator. So there is a summary for GPU and CPU, like nice diagrams for device self-time, device total time, similar for host. And there is some stack of operations which were done, which you can just analyze. And I think is the GPU kernel. So in this case, we can examine, we can see which kernels was called, and it is really nice. So we can understand which operation after benchmark and which operation was called. Like here, we see that it's gem, so it's a matrix multiplication and parameters of calls, so some grid sizes and so on. So this is really nice. We can understand parameters which after benchmarking our code just got. And finally, there is a trace. So basically, it's execution trace of a program. Oops. We can increase just profile step. Here we have some convolution calls, and at stream we can see what CUDA kernels. So you can see it more deeply when you play with it. The important point here is that if you call here flow events and I think we can see what basically what Python code called. Where kernels was called asynchronously, so with these errors. Basically, that's it. What I wanted to present about PyTorch. So if you have some questions about PyTorch, maybe you can ask now or at the end. Now we would like to switch to TensorFlow profile.
Thank you, Dennis. So this is Corey Adams. I'm a staff scientist at LCF. I'm going to present the TensorFlow profiling tools. If you are in the GitHub repository in 09 profiling frameworks, there's a TensorFlow folder. There's a lot of examples there that we're going to run during this tutorial. I encourage you to follow along. If you have issues with anything, please speak up or put it on the chat. So for profiling TensorFlow, if you see my screen here, we're going to profile again a generative adversarial network. I made some images of the final product. It's an okay GAN. It doesn't do a great job, but there are some passably legible digits it produces. The script that created these is called traingan.py. So if I'm on my Theta GPU node.
Corey, would it be possible to increase the font size?
I'm already doing it. Yes, thank you. Can you see?
I can see, yeah. You may also want to quit your mail so you don't get the notification.
Sure.
Thank you.
Okay, so here we are in the Computational Performance Workshop GitHub, and I have a script, traingan.py. If you run it, and I'll walk you through the script in just a second, we'll get an output after all it starts up, and it will tell us its throughput in terms of images per second. And the first thing we'll have to decide is this good or not? Is this a good performance? Okay, so now it's starting to run. It prints out this tuple of numbers is the epoch and the iteration, the batch within the epoch. It gives us a generator loss, a discriminator loss. Now, if you're not familiar with the two losses of training a GAN, don't worry. How long it takes to do a step, so just over half a second per iteration, and the throughput, 236 images per second. It runs for one epoch. You can quit it anytime once you've got this. And just to show you where we're going, there's a TrainGAN optimized. You can run this as well, and we'll see after all the optimizations we apply, what's our throughput going to be. Okay, while this is running, let me tell you a little bit about this script. So it's a generative adversarial network. It has two main networks. There's a discriminator here, and there is a generator here. The way a GAN training works is it's a zero-sum game. You train a generator to fake images, and a discriminator classifies them as real or fake. And the better the discriminator, the better the GAN can get trained. Okay, here's the optimized version going. So it's already on epoch 8. The throughput is bouncing around between 140,000 images per second and 100,000 images per second. So that's about 500 times faster. So over the course of the next 25 minutes, I'm going to walk you through all those optimizations to get from the starting point to the end point. So the training script for this is pretty simple. This script starts up and it calls this function train_gan with a batch size of however many training epochs it wants. Inside of here, this train_gan function, it creates a generator, initializes the generator with some random input. It creates a discriminator, initializes the discriminator with that randomly generated image, and then creates optimizers, Atom and RMS prop, one optimizer for each of the networks, and then it goes through this training loop. Inside this training loop, it just loops over the epochs, and for each epoch, it does this double pass through the networks. It does a forward pass for the generator first, and then it computes the trainable variables, gets the gradient, and applies it. And then it uses the discriminator, forward pass, trainable variables, gradients, apply them. And that's it. This is the GAN training loop. The very first thing we want to do to see what our bottlenecks are is to use Python's line profiler. So if you go into this script, this folder line profiler in the TensorFlow folder, it will have some examples for how you can actually use this. I'm running in a container here. I put one in the computational performance workshop. I got a more up-to-date container than the one in the README. You are welcome to use this container. This container here will also work just fine. So I run this. If you get these errors, don't worry about them yet. I'll have to check my directory. Okay. The line profiler tool is a simple Python instrumenter. It will look for these decorator functions. If I open the code inside here, it's the same script, but I add some functions at profile. If you're not familiar with decorators, they're a Python syntax that basically replaces a function. It takes a function as an input and gives a function as an output, and it changes it a little bit. So in this case, it's telling Python to decorate this function with profiling hooks so that the line profiler, when it runs this function, will measure how much time each line takes. It's pretty high level. It's only Python calls that get profiled. You don't know anything about what's going on under the hood. So if you're using a library like NumPy, TensorFlow, PyTorch, you don't know any details about its performance. But it does let you identify quickly some high-level bottlenecks. So I decorated 3 functions. I did my main train_gan function. I did the train loop, and I also added the forward pass function up here, which I'll walk through in a second. So to run this, you do kernprof-l. Kernprof is short for kernel profiler. I think it's a Python package. There's installation instructions inside the line profiler. If you're using the same container as me, this one in the computational performance workshop, I pre-installed it, so it's good to go. You do kernprof-l for line, and then you do train_gan.py. So this will run for a few seconds. You'll want to let it get into a few iterations of the training loop. And then at any time, once it's running, you can Control C, and it will still spit out the profiling information after it interrupts the execution. Okay, here it goes. So if you recall, the main script was about 237 images per second. Now we're at 224 to 25. That's expected because profiling does have a little bit of overhead. So we're getting a slightly reduced throughput overall now that we've added the profiling. So this is almost completed an epoch. I'm going to go ahead and Control C. Gave me this note that it wrote the profile results to train_gan.py.lprof. You can view those very easily with the line profiler module. So if you do Python-m for module line profiler, and then you just pass it this function, this file, it will print out something that looks like this. So it's echoing back my Python code, except now it's giving me these numbers where up here at the header, we can see what it is. So it identifies the line in my file, how many times it hit that line, how long that hit took, as well as the time per hit, and then what's the breakdown in percentage. So it spent about 20% of its execution time initializing the generator. That's okay. That's not much. There's not much we can do to optimize that since that's just startup cost. And then this first pass was also a bit of a hit as it got all the kernels ready on the GPU. And then the rest of the time it's spent in this train loop. So that is about what we expect. Looking at the train loop function, as we scroll through, we see that 88% of the time is in the forward pass. Okay, that seems like it's good. And 10% is in applying calculating the gradients. That's the backward pass of the network. And then just 2% in applying the gradients. If you're familiar with training a neural network, seeing 10% here and 90% here, forward pass versus backward pass, that's a little concerning because the backward pass is usually more computationally intensive. That means to me there's some sort of bottleneck that's not well optimized in the forward pass. Yes, to answer your question, Alfred, on Slack, you do need an interactive queue sub for the TensorFlow examples. Okay, so if I look at the results of the forward pass function, here it is. So what's this function doing? It takes in the two networks, the generator and the discriminator. It takes in the batch size and it takes in an input size. So that is part of the GAN. You give it a random number of random numbers. You can determine how many numbers you feed it. That's the input size. Okay, so 92% of this function is in this call fetch real batch. That's getting the real data. So this means that our network is IO bound. The rest of the time, 3.4% of this function is in generating the images, 2% each on discriminating the images. And if that's effectively it, there's very little other time spent in this function. So let me look at this function here, fetch real batch. That one's right above here. It's pretty simple. It gets a train and the test data set, calling this get data set function. It chooses some, it reshapes them and returns them. This get data set function up here, looks to be loading the MNIST data set every iteration. So that's the issue. It makes absolutely no sense to load the data set every time. This is somewhat of a contrived bug. Most people, I think, wouldn't write this code. I wrote it quite poorly to start, so we'd have a good optimization path. But there's a better way to do this. In the same line profiler folder, you can find this function trainGAN_IOFix. Oh my, there we go. It crashed a little bit. Okay, at the top of this function, I've moved the dataset loading up here, and I convert it to tensor. I convert the train data to a tensor. I shuffle it, and I make it into a TF dataset. So instead of loading it each time, I'm now just going to be pulling from a dataset. I give it a shuffle, and I change the forward pass function here. Instead of calling get data every time, I just pass it a batch of data. Everything else in here is basically the same. And inside the train loop, I pull a batch of data from the data set each time to give it to the forward pass. So I've now taken all of that IO overhead from loading the MNIST data set every iteration and moved it up front once in a startup cost so that our iterations are much faster. The IO fix is also decorated in the same spots with the profiler hooks. So I can run this same command, kernprof-l train gan iofix.py, and we'll see what we get. So right off the bat, with no changes except to IO, we're running about 10 times faster. All right, so I'll control C that. And I will open this with Python-m line profiler. Okay, so similar distribution here, a little less time starting up the generator, a little more time the first time through. Still spending most of our time in train loop. Again, that's kind of what we wanted. Now when I look at this train loop function, getting the data set is very quick to shuffle. Pulling the data, not so bad. And then half my time in the forward pass and about a third of my time in the backward pass. So we're getting much closer to an optimized and balanced implementation here. This right here, 45% in our forward pass. If you look at this, Most of our time is still spent in the generator, the discriminator, both times. So that's 40% plus 25 plus 25 is 90% of our forward pass is in these three calls. And then just a little bit in these loss computations. In TensorFlow, the way that a network is run in eager mode is it will actually call a Python function, and it will go through, for example, this one is the generator. Yes, so it will take inputs and it will go through these loops. And each time it finishes an operation, it goes back to Python, goes through some control statements to get to the next layer, it goes back down into the CUDA kernels, runs your layer on your GPU, and comes back to Python. You can optimize that in Python or in TensorFlow through the TF function interface. So this is what we'll do next. If you're following along on an interactive node, head back up to the main folder and go into this TF function folder. Okay, so I have the same implementation that we fixed with the IO in here, but now I have these decorators at TF function. So this is a TensorFlow syntax. Just like the profiling hook was a decorator and took in a function and returned a function, this is doing the same thing, but this is telling TensorFlow, the first time you go through this function, trace everything that happens, and instead of going back to Python for each subsequent call, just make a graph, a TensorFlow graph, so that you take the inputs, do all of these operations within TensorFlow's C++ API, and then give you back the outputs in Python. And these get nested. So I put one on the discriminator, I put one on the generator, their call functions, which is where they're actually computing. I put one on the loss function, and I put it on the forward pass. Now here's a detail that's a little tricky. The forward pass I had before used some NumPy operations, for example, generating random data, creating zeros and ones. All of this has to be converted to TensorFlow operations, because if you leave them as NumPy, they'll get called once on their first pass through TensorFlow, and then that output gets saved as a constant. So if you're doing random numbers, that's quite bad. You'll get terrible results. You need to convert these to TensorFlow. Each time it goes through, it will nest this. So if I hadn't put something on the discriminator and the generator, it actually doesn't matter. TensorFlow will try to apply TF function to everything within this function that you've decorated. The last thing I did is in the train loop. I made this training iteration into its own function. So this function is within the context of the other function. So it only exists inside this train loop context, but it's called train iteration. It takes the data, models the optimizers and the global size if it's data parallel. And this is so I can do the forward pass, the gradient calculation, and the gradient application together. TensorFlow doesn't like the loop I had over that list of strings, network, generator, and discriminator. So I just broke that into two pieces, update the generator, update the discriminator. And this can be compiled, graph compiled with TensorFlow. And then the actual training loop looks like this. So it calls this train iteration each time, gets the loss, and then goes on to the next match. So if you're doing this, you can run Python train-gan IO fix, and we'll see how we're doing. The graph compilation typically takes a few iterations to really get up to speed. So there it goes. Now we're running at 89,000 images per second for the first epoch. That's quite fast. One thing that we can add to do an additional compilation in TensorFlow is once you've reached the graph optimization level where you've compiled a function, TensorFlow has a tool called XLA, and you can find the syntax for this in the README for this folder. But you can add an environment variable, TF XLA flags equals this. So I'll export that. And that will take every graph compiled function and try to fuse operations. So if you have a convolution followed by an activation, it can actually fuse them into one operation, conv plus activation, run it on the GPU, and you'll get better performance because it doesn't have to do any memory access in between those operations. The downside of XLA is you will lose sight of some of your profiling operations. When we profile with XLA, it just shows up as an XLA kernel, versus if you profile without XLA, you'll be able to identify conv2d, etc. With XLA applied, we got another 10,000 images per second. So that's a nice boost. I'm going to switch folders again and look at the TF profiler folder. So this is the same code as before, but now it has an additional line. Here we go. Down in the train loop, I've added 2 lines, tf.profiler.experimental start, and then at the very end, tf.profiler.experimental stop. This is the TensorFlow built-in profiler, and it will give us the, similar to PyTorch's profiling, it will actually look at call by call what's going on under the hood in terms of CUDA operations, TensorFlow operations, and let us see a little more clearly into the problem. If you're not following along, some of these results are on the GitHub. So this TF profiler folder has some screenshots of what the TensorFlow profiler looks like. So you'll land on a splash page of performance summary, and it will give you some recommendations for the next step. Some of these are useful, some of these are not. 3.3% of the total time is actually spent on kernel launch. That's because we generally have a very small network here. This GAN is quite small compared to what the A100 can do. This tidbit here, only 0.0% of device computation is 16-bit. That's actually an important one. It's telling us we're in float 32 precision. If we went to float 16, we could get a significant speed up, it says, if the reduced accuracy is acceptable. When reduced precision is and isn't acceptable, we'll actually hear about in the next talk. As you scroll down, it gives you the list of the top 10 TensorFlow implementations. Without XLA, you'll see the actual calls, so conv2d backprop filter, and you can look at the operation and see, okay, this is conv2d_2. That's the second convolution that it was called. Here's the first one. There's a batch normalization. There's another conv2d_5, and they're all roughly equal in time, which is what we want. And they're stacking up to count for 25% of the total time is in these top 10 operations. So it looks like we have a lot of fairly small operations. Again, if you go to the kernel statistics page, you see a pretty even distribution. Just like PyTorch, TensorFlow profiler has this timeline view. It'll be a little less divided if you use XLA, because you'll just see a couple XLA blocks. But you can even zoom in and see here's a full iteration. On the top is the GPU, on the bottom is the CPU. You can see this chunk. If you see my mouse, this is doing our data loading, and then it jumps over to the GPU and does our forward and backward pass. It does the generator and then the discriminator, and then it finishes the iteration and goes on to the next one. So the last thing I want to try with you is in reduced precision. There's a pretty easy way to get to reduced precision in TensorFlow. You can make this call before you actually run anything. tf.keras.mixedprecision.setGlobalPolicy, and then you can say mixed float 16. In my script, due to the way I wrote it, which isn't necessarily the perfect way, there's a couple of float 32 ops that have to be changed to float 16. That's pretty easy to control F, find them all and fix them. If you're running in the original container I had for this, which was from February, you actually see a slowdown. And if you do the profiling, it's pretty quick to find out why. One particular convolution takes 25 to 26% of the time. So we no longer have an even breakdown, but you get one big op slowing everything down. And when you zoom into the trace view, you can see it right here. It's this massive conv2d_3. That's actually a bug. If you run in the latest container, this goes away. So giving you better FP16 precision is actually fixed in the latest version. Okay, so putting it all together, this train GAN optimized is including all of these optimizations we did. So it's got the data set loading up here. I set the XLI environment variable in the file, so it's always on. I apply all my TF function operations, and I, right here, set my mixed precision policy. So it's using float 16, and I changed all my float 32s to float 16 everywhere. So they're all fixed. And that's how you end up with going from, say, 230 images per second to 140,000 images per second. I'm going to leave time for a few questions, but I'll just throw it out there. There's an inference version of this script as well that doesn't do the backpropagation and includes all these same optimizations, which will get you for inference level up to about 400 to 500 images, 400 to 500,000 images per second in inference. This model is small and the image size is small. So one of the other optimizations you can do is increase the batch size, which in the optimized version I do. The batch size is up to more than 8,000. It's still a very small load on the A100 GPU. But this is just one example of how you can take some of your TensorFlow code and really accelerate it. So I'll leave time for a couple questions, either to me or Dennis, I think is fine.